So I'm drawing lots of pictures in lectures. That's kind of what I'm doing. The textbook, I put in the syllabus, and I want to make sure I state it here. I think I did earlier, but I prepared the lectures under the assumption that you have read or will read the textbook. So I'm not going to recite the definitions and stuff, right? You can read the definition in the textbook. And in the lectures, I'll be drawing a lot of pictures and making analogies and things to try to deepen the understanding of it. And don't necessarily just stop with what I do, because maybe there's another analogy that you could, a comparison that you could make to your own personal experiences that help you understand it a lot better. So keep looking for those. A continual progression. You don't want to just pass this class and just barely pass the classes and get the degree and then be done learning forever. You need to continually progress, especially in the field of IT. IT is a very dynamic field, so you got to keep up on the stuff. So you always want to keep looking at that. So I'm going to talk about draw pictures and talk about analogies that I found work for me. But keep looking for some that maybe work better for you. That always continuing to learn. Well, these first couple pictures aren't really analogies, just kind of a basic breakdown. So we have a few parts we're looking at. So a super basic one, we're going to break this into 3 parts. The CPU, the central processing unit, and if you're a big gamer and you games your interest in stuff, a GPU is going to be a subset of that. If it's something graphics heavy, we just do a second CPU specifically for graphics, and then our CPU can do the processing. Is the concept there. But a lot of what we talk about with the CPU will also apply to the GPU. Just slightly different focus, and a CPU can stand on its own, but a GPU usually goes in conjunction with that. But for class pictures, keep the pictures somewhat simple when we talk about CPUs. And then that big point I made earlier, electronic memory. Machines can remember what they already have done. So we have this communication going on between our CPU and memory. The memory going back and forth, CPU processing it. And I might as well fill out this picture. The other major piece we'll need for this class is going to be some sort of storage. We won't be there for a couple weeks, but we want things to stick around, right? This will run the program, but then when they send into the program, the data's gone. So we might want to keep around. So we have some interaction there going back and forth. We get our data from storage, or when we're done processing, we put the data in storage to keep it around for later. But for programmers and software developers, hence the name of this class, it's a software development course, it's a label, we mostly live up in this range, CPU and memory. So this is where we'll be spending most of our time. But a very crude picture. We probably want to be a little more detailed, right? The precise version is electrical components, so that's electrical engineering. So we're not going to get that detailed. So let me start with just a list of the major pieces. So this is the one I expect you to know, the list of major pieces. In general, I will always try to show more than what I grade you on, right? So like here, this picture I'm getting ready to draw here is what's going to show up on the quizzes and stuff, which is just a list of the pieces inside the CPU. The next picture I draw is starting to get into deeper understanding. That's what you'll need in the long run for your degree. But for now, we need to know what pieces are in there. So there's going to be a few. I'll draw it in a box here, just to kind of keep the picture thing going. Obviously, we need some way to control it. So our main piece will be a control unit. Something that's controlling everything and tying it together. And I'll just bring this in here and put I'll put random access memory, RAM. Random access, that's our general memory, hold for a second memory, and then we'll grab it back when we need it. There's also read-only memory, but anytime we talk about read-only memory, it should be obvious in this class. So I'm just going to label things with RAM for this class because we're talking about programming, so we're going to talk about the temporary one. This piece called registers. That's supposed to be an E. Doesn't really look like an E. So registers are basically another holding spot for our data. Another holding spot as it moves through. I've got some supplemental material I'll talk about in a moment, where I talk about those in a little more detail. For now, I just want you to be aware that that's a key part of the CPU. Then we have the ALU, and that stands for Arithmetic Logic Unit. Logic Unit. That's the piece that does math. We send in two numbers, it adds them together, or adds them a bunch of times to get multiplication. And we also, along with that, have a floating point unit. So there's really going to be two separate parts, whether we're working with whole numbers or fractions, decimals. Because we don't really display them as fractions usually, but the decimal numbers. We are FPU, and then we need to synchronize everything together. That's an important part in any electronic device we build, is we need to set up a clock signal. Not like the wall clock that tells us we're running late for work, but just a clock, something that synchronizes everything together. So when we talk about computers or electronics in general and mention clock, it's not necessarily, the thing saying on the wall saying 3:15. It's a steady signal that'll tie everything together. And again, it's controlled by the control unit. So it's maybe not even a steady signal, it's just a signal that lets everything know that it's time for the next step. Something to synchronize it all. So that's the parts. You might want to go a little bit further and look at how they interact. So the quick starting picture I draw for this, I'm going to start with input, kind of like that big picture we had a moment ago. Have some sort of input. Then that gets pushed onto RAM or into RAM, the memory. That gets pushed someplace where we can hold it. And it's just going to sit there until the control unit is ready for it. And then the control unit will pull it from RAM. And there are more parts. This is a simplified drawing, just introduction to it. And it will push it onto either the ALU or the FPU. Arithmetic logic unit or floating point unit, depending on if we're working with whole numbers or decimals, whichever type of math we need. The control unit will push it on there. And then from that, it's going to go to the registers. We get pulled into the registers. And then the control unit will make a comparison. If it's done with it, all the math's done, all the processing's done, it's going to get pushed to the output. I'll draw a line there. So that's the general flow of data. I kind of like you to know this, the basic idea. This is the requirement. This is what there's going to be questions over, what are the names of the pieces in there? Here's how they go together. And one of the key points I want to note here. Notice where how I put push and pull all over the place. For example, the ALU and the FBU. Things are pushed onto them and pulled out of them. They don't do anything but sit there themselves. Oh, I guess I could add to this picture. If the mat's not done, the control unit will push it back. The control unit's doing all the pushing and pulling, but the control unit will push it back in to those to see if it needs done, and then run the next step, and then check again. Eventually, the mat will get done. But some things have data pushed onto them and have data pulled from them, but they don't do anything but sit there themselves. The control unit is what does all the work. It's pushing and pulling the bits around and sending them to where they need to go. So starting with a general flow of data. And obviously a very crude rudimentary picture here. So for years, since the first time I taught this class, the next step is I say, if this is along the lines of interest and you want to know more about this, a Wikipedia page has an excellent picture that's a step beyond this, that's still not super complicated. It's still a step beyond this, but a step below electrical engineering. So you can still follow just the arrows around. Just list out the pieces, has the arrows flowing around. And I'm making these videos a couple weeks before the semester starts, that way they're ready for you. But the picture's there today, and that picture's been there for 6 years, 7 years. So I'm going to assume it's still going to be there. It's a really nice picture. It's kind of like this, just a rudimentary picture showing the pieces and arrows showing the flow of data between them. Well, a step beyond this, but still a couple steps below full-blown electrical engineering. And also, I'll take that to introduce this little supplemental material I made. For some things, questions that have been asked before, or questions I anticipate some people might ask, since we're not in a classroom where we can, directly interact, you can send me emails, text messages. All my contact information is in the syllabus, so I'm happy to help anytime. Just send me a question. But some of the anticipated ones, I went ahead and made some videos for describing it in a little more detail. For example, registers, that's just a word that's going to show up in this course. We're going to mention it a lot, but never really describe what it is or what it's doing. So I made some supplemental videos to cover that stuff. And I included the link. I think the link I put in Ivy Learn goes to the introduction on that, and it's like a 3-minute introduction video, and that's for people that stumble across them online. You don't have to skip over the introduction video. The rest of them are just slightly more in-depth with questions I've heard before or questions I anticipate. And I went ahead and put some supplemental videos to get a little more in-depth if you want to watch those. But obviously, again, that's a step beyond. If it matches your interest in computers. So just kind of some starting pictures about what's going on. The CPU, we don't want to just say there's CPU. We want to break that down and at this level at least know what the main components of a CPU are. Know what those are. And I'd like you to kind of have a basic idea of the flow of data through how data flows through a machine. Is that everything I had on there? You refer to the Wikipedia page, and then I'll do those. Oh, one more drawing. I'm not going to draw this every time. So I'm going to introduce you now to the picture that I will be drawing a lot when we're talking about CPUs. And all right, a big cheer for the power of editing. Videos do provide some things that aren't available in the classroom. So jumping back in here with some editing, and you have the same thing when you're at home, right? In a classroom, we don't show up at the same time, sit there, go through all this, then head home afterwards and just have the notes you took in class to work with. But with the video, you can pause the video, rewind, watch it again, that sort of thing. So I had to do some editing, so I thought I'd mention that there. So the picture I'm going to use to refer to this process most often is what's known as a stack heap diagram. This is kind of a standard picture. So there's two parts to it. Over here, there's a section that has a definite bottom. So it's like a starting point. Whereas this one's just open on both sides. So this is the stack. And a stack is one of the ways we process through data. The standard example for it is like a stack of plates. After we finish washing the dishes, we go and stack the plates up in the cabinet. And then when we're ready for our next meal, we just walk over to the cabinet and typically grab the top plate. So the last plate to get put away is the first plate to get used. And that's the most common way that computers do processing. So a last in, first out way of processing. Or for the quick introduction here, this is where we put our program. So this side, the stack, will represent the stuff in our program. And then over here is heap, which is another way of processing. And a heap is dynamically allocated. So it's dynamic, it changes. It's set up to change, it changes while we're doing stuff. The computer keeps track of the heap. But a stack representing our program and a heap representing memory when we're doing processing. And basically what this will look like is, maybe we have some variable called x over here that we use in our program, and that points to some block of memory. 2, 3, 4, points to a block over in memory, a bunch of bits that actually are the actual version of the data. But the computer keeps track of that, right? The computer might know that as something like, I don't know, maybe it's bit 89,243. The computer has no trouble remembering where that bit of data starts at, where the first bit of that data is. But us, on the other hand, we'll never remember where that data starts at. So we give it a more useful name. We'll talk about that soon. And then that's represented with this picture, the stack represents our code and the names that we give things, and it points to a spot in memory. So that's the picture I will use to represent this as we talk about this stuff in class. So that gets the setup. So I guess the next thing is kind of getting started into the basic idea of how do we give these instructions to a computer. All right, so now we're ready to start feeding instructions into the machine. Got a little bit of setup out of the way. Well, some more setup. What do these machines do? So you've probably heard this word before. Binary. So first off, binary is not a computer thing. Computers make use of binary. Binary means two states, such as on, off. That's typically how we're going to refer to it. More precisely, it would be high or low voltage. We'll talk about that here in just a second. True, false. Yes, no. The whole black and white world. It's one or the other. Two states. That's what binary means. And typically we're going to represent this in computers with a 1 and a 0. And we do that because 1 and 0 are quick, easy symbols to write that we can tell immediately at a glance which one's which. We define the meaning on them, but when we're putting things together, we might have to use different words. We're not going to pick one of these sets and use that. We're not going to go with on, off all the time. Because sometimes yes or no will make it a lot more sense out of it. True or false, high or low is the actual state. Because remember, it's an electrical machine. So what we have is some sort of voltage. So I'll draw a plot here of voltage over time. As our time moves forward, we have our voltage could be at different levels. And what voltage is electrically is voltage is a potential for electricity to flow. So this one's a lot easier to control. It's the potential for something to happen. Another common example in physics, Up on a windowsill, stick a flower pot sitting on a windowsill. Right? It's several stories up the building. Gravity is pulling down, right? So there is potential that something could, if a cat bumps that flower pot, there's a potential gravity could take hold and it could fall. A potential for it to fall, but it's not actually falling yet. So that's what voltage is. There's a potential for electricity to flow. Once it flows, we call it current. But that part happens very, very quickly. It's hard to do stuff while the current is flowing. So we control the voltage. And really what we do is we put some sort of threshold. And then our voltage is either above or below that threshold. Most processors nowadays are going to be at 1.2. 3.3 volts is still very common, and 5 volts, 1.2, 3.3, 5 volts, those are probably the three most common voltages. Very low electricity, right? That's why we do analogies, because it's hard to visualize this. This is very, very low levels of electricity. And there's more electricity when you walk across the carpet, right? Shock yourself on the doorknob. That is way above these levels. So these are very, very low. So it's hard to visualize it, right? We can't visualize 5 volts. That's not even the same as getting shocked by a doorknob at the edge of the living room. So that's why we do analogies, not draw pictures to describe this stuff and not develop the understanding. But we set up some sort of voltage threshold. And then we can control that voltage so that things are either below the voltage or above the voltage. Below the voltage, above the voltage, and it bounces around, so it could be something like this, back down. So as it progresses over time, we have either a high voltage or a low voltage state. But typically we would say on or off. The high voltage above our threshold, that means there's enough to turn on a component. And low voltage, below the threshold, that means there's not enough to turn on our component, so it's going to be off. But in some situations, true or false, yes or no, or different binary terms might be better for understanding. So that's going to change situation to situation. And as far as this, we represent it with a 1 and a 0. For the most part in this class, I'm say a 0 is off and a 1 is on. And the times that it's different, I will make sure and state that explicitly. So we're going to use a 0 for off and a 1 for on. So here it's below the threshold, so it's off. Then a split second later, it's above the threshold, so it's on. A little bit later, drops below, so it's off, goes back on. And here it didn't go all the way down, but it did go below the threshold, so that's off. And then it goes on again. And then that's where our binary states are, the ons, offs, 1, which we represent with 1 and 0, because we can write a bunch of those very quickly, easy to write, and we can tell at a glance which one's which. So that's how we represent our data, the 1s and 0s. But as we do things with it, we want to apply different meanings that fit the situation, and we can help develop the best understanding of a particular situation. Okay, so the computer has this state of ons and offs, high voltages and low voltages, where once the current starts flowing, if it's a high voltage, the current's going to flow that path. If it's a low voltage, the current's not taking that path. And we're going to represent that with a bunch of 1s and 0s. Where'd my notes go? Here we go. So I'm going to copy this. I copied this example. So the machine is going to have something like this. 1 1 0 1 0 0 1 0 1 0 0 1 1 0 1 0 0. So the machine is going to have something like this, which we look at that, have no idea what that's saying, right? And this is what's called machine language. This is what the computer is actually processing. And not just that, that's not a specific thing. That's not a general thing. That is specific to a machine, a certain machine. If we put that instruction into another machine, it would do something different. So that you have to know what machine you're on and what the instructions are for that machine and everything. So if we look at that, there's a lot of different ways we could take that data and translate those ones and zeros into something that has meaning to us. So machine language is really hard to work with. So for human benefit, early programmers developed what's called assembly language. I say programmers, this is still completely electrical engineering. This is halfway between electrical engineering and what we would call computer fields. So the electrical engineers put together what's called assembly language so that humans could work with it. In this same instruction on the same machine, I copied these examples. The human would type in something that looked more like add 0010 0011 result. So this is what the human would type in, which would get translated into this on a particular machine. Alright, so add, and then on that machine, people working in assembly language would know if we saw binary, then that's representing a number. In this case, that's 2 and 3. We'll go over that very soon, how to interpret those numbers. And then result, I'm just going to write an equal sign. We're going to talk about an equal sign here in a moment. But that's what the instruction the programmer would feed in. And notice the order it goes in. Because if we were writing that, we would write 2 plus 3 equals. But the machine needs to know the operation first. Because some operations take 2 numbers and some operations only take 1 number. If we're going to square a number, all we need is the 1 number that's being squared. So the machine needs to know the operation first. And when it says add, that's 2, takes 2 numbers. So then the machine's going to know that the next 2, in this case 4 bits, chunks of 4 bits that come through will be numbers. So the binary representation of 2, the binary representation of 3, and then the final instruction, which on this particular machine was print the result. So that's what it looks like in assembly language, a little bit more human-friendly to work with. Still not quite not quite the way we do things, right? Like I just pointed out, we would write 2 plus 3, not plus 2, 3. So that's where we get to high-level languages. So in a high-level language, this same instruction might look something like this. X equals 2 plus 3, and I'll put a semicolon here. So what this is saying is the type of thing we have. So it says we have an integer. If we add 2 integers, the result's going to be an integer. So we have an integer. So set up enough spot, tells the computer to set up enough space in memory to hold an integer. Then we're going to call it x. That way we don't have to refer to it by bit number. We don't have to remember exactly where it's at in memory. And the computer can move it around to make things more efficient if it needs to. And we'll just refer to it as x instead of the bit in memory that it's stored at. This one, I don't want to say equals here. I'll come back to that. But then 2 plus 3 is the way we would normally write that instead of plus 2, 3, the way the computer needs it. So the equal sign, we're going to refer to that does not mean equal to. So when we're doing programming, 1 equal sign I'll write down here, 1 equal, that means assignment. And 2 equal signs, equal, that means equal to. Those are not interchangeable, so you have to be careful with them. So 1 equal sign means assignment. So we would read this as integer x, I'll put quote marks around it, this is how we would say this. So the integer x is assigned 2 plus 3. So that's how we would actually read that statement. And that's kind of a key point. 1 equal sign means assignment. So take the value, take 2, add 3, whatever value that gives, assign it or store it in x, which is going to be an integer. So we read it that way. And that's a high-level language. It looks like what we're used to doing. So that's what we're going to focus on in this class. We'll get started with some high-level languages. Yep, so next page says first program. So we're ready to jump into an example now. So, a whole lot of lead in, but now we're on to doing stuff. The fun part. Some of us find it fun. Some people maybe not so much, but for some of us, programming, I enjoy it. It's like a game. It's like a game or a puzzle, and very rewarding when all the pieces come together and see it work. Some of us enjoy it, some people don't. So I hope you enjoy it, and try to approach it like a puzzle. Have fun with it. Get excited as you're putting the pieces together. That's how I approach it. So we're ready for our first example. Gonna do some pseudocode and talking about things, and then we'll do a screencast and walk through the example.